So this is number 36 from chapter 17. It's on page 403. It covers a lot, both geometric and binomial questions. So this is about a disease called rickets. It has to do with vitamin D deficiencies. A study showed that 20% of British children are deficient in vitamin D, and we're going to test some elementary students. So the first thing we want to check is this a Bernoulli trial. Are there two outcomes? Yes, you're either vitamin D deficient or you're not. We can assume there's a constant probability, particularly for testing elementary students randomly. And do we have independence? Well, certainly we'll be testing less than 10% of the overall population. So the first question we encounter, and this is a lot like the seatbelt question, I think it's 31, or the left-handed, this will get into the left-handed question as well. There's the last two problems on chapter 17. This should help you with those, and the others if you haven't done those yet. Okay, so what's the likelihood that the first student we find who is deficient is the 8th one tested? Well, we're using a geometric model where the likelihood of being deficient is 20%, and we want to know what's the likelihood that that 8th person, in this case with a geometric model, the probability that x equals 8. We're looking for success, essentially, on the 8th person. Well, what does that mean? It means that the first 7 were not vitamin D deficient. So that's 80%. And then finally, we got 20% on the last person, and that works out to be 0.042. So the first 7 weren't deficient. That's 80% of the population. And finally, on the 8th student tested, there was quote-unquote success. So if we go back to this, so our Q was 80%, and that was, since 8 was our x minus 1 is 7, and then finally we had success. So that's how that formula works. But it's also just sort of common sense. What's the likelihood that the first 10 are okay? We don't really have notation for this, but what does that mean? That means that we got 10 in a row, not deficient and not deficient and not deficient and not deficient 10 times. So that's just 0.8 to the 10th, which is 0.107. And then we come to this idea of an expected value or a mean. How many do we expect to test before we find the first one deficient? Well, again, that's our 1 over p, which is 1 over 0.2, which is 1 in 5. This is 1 in 5, right? And so this is just 5. So we would expect to test 5 kids before we found the first one deficient. So these are all geometric probabilities. They didn't ask for a standard deviation here, but there is a standard deviation formula for that. There's our mean, 1 over the likelihood of success. Okay, the next involves some binomial questions. So D says, okay, we're going to test 50 students. What would be the mean and the standard deviation? So I'm going to use Y here, Y being the number of children who are deficient out of 50. So it's a binomial model because we have a specific number of trials with a success rate of 20%. So this is pretty simple. This is just this idea of n times p. The number of trials in this case is 50 with a success rate of 0.2. And what does that give you? 10 children. So on average, if we test 50 students, we expect 10 children to be deficient. And what's the standard deviation of that? That's just the square root of n times p times q. Again, those are down here, square root of npq. And that works out to be 50 times 0.2 times 0.8, which is 2.83 students. So we'd expect out of 50, 10 children to be deficient with a standard deviation of 2.83. Now here's where where we might need to use the normal model. So in this case, we're going to test 320 students. What's the likelihood that no more than 50 are deficient? This is going to cover a few things. So here's my binomial model. Now I have 320 students, and again, the likelihood of success is 0.2. And I'm looking for the likelihood that no more than 50. So that, I believe, is that less than or equal to 50 students. So this goes back to the binomial model. I could figure out what's the likelihood that none of them were deficient? What's the likelihood that one of them was deficient? What's the likelihood that two of them were deficient? And I would have to do that all the way up to 50. That's pretty tedious. Who wants to make those 51 calculations? But just to remind you, I would want to know how many ways would we get 0 out of 320. And if that were the case, then 0 of them had success and 320 of them were not deficient. In this case, what's the likelihood? And how many ways can none of them be deficient? That can only happen one way, where no one in the whole row of 50 is deficient. How many ways can only one of them be deficient? That would be 320. And again, in your calculator, that'd be N. N would be your 320. NCR, 320. Then you'd hit this button and 0. Sometimes we say 320, choose 0, and that'll return the number of ways this can happen. So again, in this case, 1 would be successful, and then 319 would be failures. And then in this case, how many different ways, if I have 320 students, would 2 of them be deficient? So that means 2 of them were deficient, and 318 of them were not, etc., all the way to 50. So that's tedious. So here's each of these little calculations is this. How many ways can this happen? How many ways can 2 of them be deficient and 318 of them not be deficient? And this is just another way of making that notation. Because this is yucky, I can use the normal model. Again, we check the assumptions and conditions. Would we get at least 10 successes and at least 10 failures? Yes, 20% of 320 is greater than 10, and 80% of 320 is greater than 10. So what is our mean and standard deviation? This is N times P, so 320 times 0.2 is 64. So the mean here is 64. I want to know what's the likelihood that no more than 50 are deficient, so I'm looking for this probability. So I need standard deviation, which is 320 times 0.2 times 0.8 square root. And that works out to be 7.15. Now, you could find a z-score here. Remember, a z-score would be 50 minus 64 over your standard deviation, and then find the likelihood of that z-score. I'm just going to use my calculator and say, okay, I'm looking for normal CDF, and my lower is 0. Whoops, I already did this. My upper is 50. Can't see this. My mean is 64 and my standard deviation is 7.16, and I paste that and it tells me the likelihood of that. The area under the curve here is 0.0252. So the probability that x is less than or equal to 50 is 0.0252. So there's only there's a less than 3% chance that I'm going to find 50 or less deficient in vitamin D. And I have a new operating system. If you have an older one, you do normal CDF, and then you have to give it the parameters. My low was 0, my high was 50. I had a mean of 64 and a standard deviation of 7.15. We could have done like a negative, if we were using z-scores, we'd have a negative 99. I didn't figure out what that z-score is. It's negative 1.96. So I'm going to go to negative 1.96 with a mean of 0 and a standard deviation of 1 if you're using a z-score, and it'll return this value. And then finally, if you go back to these notes, actually these are about geometrics, but you can do the same thing with binomial. I'm going to say, let's see, I have a binomial CDF. PDF gives you the exact percentage. And how many trials do I have? 320. What's my P? It's 0.2. What's my X value? 50. And since this is CDF, it's cumulative, so it's up to 50. And if I paste that, a little different. I get a slightly different result, but pretty similar, 0.027. You can play around with those. Yeah, the calculator notes just give you for geometric models, but you can apply those to binomial models as well. So I hope that covers it. Use the solutions manual. So I did 36 about rickets, which is very similar to the one about seat belts. When you're doing the problem about left-handed people getting a right-handed seat, you could do, so when you're trying to do number 31, if you don't want to spoil it and you like to use the solution manuals, check out the solution for number 32 about no-shows at an airport. Very similar. I know how many passengers I had. I know how many, I sold more tickets than seats, but I know how many people are likely to not show up. But then what's the likelihood that someone might get bumped? Again, you can use a normal model for that because you'll have a mean and you'll have some standard deviation, and you can figure out what's the likelihood that I'm going to have more than this number of people. Okay, have fun with that. Chapter 17 needs to be done by the end of, by January, I don't know what that is, 7th? Who knows? The end of NORAM week. Okay.